Awesome. Thanks so much, Rich. Hello, everyone. I'm Max Grover. I'm a atmospheric data scientist at Argonne National Laboratory. And for today's discussion, we'll be talking about the Open Radar Stack, bringing weather radar data into Pangeo. This will kind of be a broad talk about a bunch of the different tools that we're working on. I'm only one person working on this team. You can see some of the other team members listed here, especially shout out to Kai Mulbauer, Alfonso, who's on the call today, as well as Scott Collis, Zach, Bobby, Joe, as well as the broader Open Radar community for making all this possible. Let's dig in. So weather radar data, what makes this data unique and why do we need toolkits to work with this? So this is a video from the COMET program, the MET-ED module, sort of showing how radars work. And it's a meteorological observation network and an instrument that gives us information mainly about precipitation in clouds. So you can see the radar scanning here. This was originally developed during World War II, where they basically you emit microwaves and it measures the scatterers that come back. So it goes through these different elevations, what we call basically how high the radar is tilted around. You can see it start at the beginning. It starts at these lower levels at that half degree, kind of right along the horizon, goes up a level, sweeps around. And you'll notice that just by the nature of the beam that it spreads out as you go farther from the radar. And so you get this sort of irregularly shaped data. It's stored basically by each elevation. It's basically a single unit. And yeah, it's a super useful measurement, especially within the weather community, but even there's a lot of other communities that use this. For example, you can use it to look at like bird migration, since the radar beam will run into whatever it's scanning within the atmosphere. So this is also another example of sort of what the data looks like. So you can see as you get farther, the radar would be located here at the 0, 0 coordinate. As you get farther from the radar, the data spreads out more, and you can also tell that it gets higher in the atmosphere as you get farther away. So that's an example of a scan strategy. This is from actually from Radlib, looking at the difference. That's your 1 degree, your 2 degree, your 3 degree, all the way up to like your 28 degree, and that's in reference to your horizon. So that's a little bit over. I know not everyone here has heard or worked with weather radar data, so I figured it providing a little bit of background on what we mean and some of the core data structures here. So let's talk about weather radar data in Python. So the first kind of Python toolkit in the space, and one of the first within the space, specifically within Python, was the Python ARM Radar Toolkit. This was originally created by Scott Collis and Jonathan Helmus in 2013, but has been funded by the Atmospheric Radiation Measurement User Facility, which is a Department of Energy user facility. And it was made to work with a lot of the ARM research radars at first, because they set up all these new radars and people needed tools, especially the research community, to be able to work with them. And then since then, there were other radar data formats supported through XRadar, which is the US National Weather Service, as well as a lot of European weather radars. And there's 13 other radar formats that are supported. Since the creation of the package, it's since had over 300 peer-reviewed publications that have cited it, has quite a few downloads, and really was a good model of trying to figure out how to load data into a common representation, which in PyArt's case is this radar object. And then you can go off and do your retrievals, your gridding, your corrections, visualization, and so on. But we know that there's a lot of other packages that have developed since that 2013 timeframe. And this isn't the only one within the Python space. So I put the Open Radar community because there's a lot of other packages within the radar community that people are working on. This is similar to some of the graphics on the Pangeo site, sort of showing what we mean by like the stack here. So looking at common data models, like I mentioned, the PyArt radar object. You also have Radlib listed here, which works a lot with xarray. We also have ND arrays. You can either use NumPy or Dask. processing mode, being able to support it through either Jupyter or through batch, and then also working on the HPC and cloud platforms. And what I just talked about was PyArt, which is one piece of the Open Radar community that works with the Python programming language. But there's also RadLib and PyRad, which are other toolkits in the space that work in Python. But then we also have a lot of non-Python folks. So LROS predates PyArt by quite a few years. And that's more of a C, C++, more of a command line type tool, as well as some different GUIs that people can use to explore their data. Then you also have BaltRad, which is a little bit more operational focus, which again provides a lot of GUIs and also basically a lot of like bash scripting that you can work with things. So what we're really aiming for within this community is common data models, and trying to find a nice way of playing well with each other, and trying to find commonality, especially on that data model side of things. And so you might be wondering, why didn't we just use Xarray as the core data model? Why do we have this PyArt radar object when we have Xarray? And like I said, PyArt started in 2013. That's when the first iteration of the radar object was created. And that was sort of pre-Xarray. Like Xarray was in the very early stages, and Pangeo hadn't really become a thing yet. So yeah, that sort of standard and just sort of the paradigm of having a common data model, which in the Pangeo community is the Xarray data model, and having a whole suite of toolkits to work with the Xarray data structures and that sort of thing just hadn't really existed yet, which is the focus of today. Sort of talking about this initial issue was created in 2017, trying to do this. And here we are in 2024, still talking about it. So like I mentioned before, the typical Pangeo workflow, you have some sort of data, whether that's in the cloud or on some HPC system or on your local machine. You get things into Xarray, you use Dask or whatever your distributed scheduler of choices. You have your Jupyter notebook or your Jupyter Hub or Binder Hub or whatever you want to use, and then you have your end user. So then there's a nice community of practice, which again, all of us are very familiar with. But the problem is we have all these different radar data formats. We have some that are NetCDF-like. It's a special flavor of NetCDF that fits the different sweeps and everything in there. We also have a whole variety of binary data formats that are each specific to different vendors, because each of those instruments has a company that makes them and generates the software, and it's not all the same. So especially with the creation of data tree and this new data model, the CF-Radial-2 FM301 standard, which basically uses HDF groups, we came up with XRadar, which is basically an in-memory representation of the FM301 CF-Radial-2 standard, which basically stores, the idea is that each of those elevations, like I was showing before, like sweep 0, sweep 1, sweep 2, so on, would be stored in its own node within the data tree. And then you can easily save that out, and it conforms to the CF-Radial-2 standard, where you store those in their own HDF groups. And so we created this XRadar toolkit, which uses data tree, and we've been following along with the main Xarray repo to see using it within Xarray itself. And so the idea is that we need to develop these backends. So each different data format has its own associated backends, and XRadar is basically a library of dedicated backends to support all these different data formats. So for example, like when most people use Xarray and are working with especially climate model data sets or other Earth observing data sets, a lot of the time it is NetCDF4, where you just sort of use the NetCDF4 backend by default. We're working on these radar specific ones, like NextRad Level 2, which is a National Weather Service data format, and also IRIS-SIGMAT, which is used by quite a few different, especially a lot of the bicycle radars, where these are all byte encoded binary formats, where we write the Xarray backend and then it gets it into your Xarray data set. So far, some of the common data structures that we have reading in is CF-Radial-1, which is a specific flavor of NetCDF that we load in there. We also have Iris Sigmet, Rainbow, Odom H5, Gamma, Furuno, and then XRad level 2. We're working on an XRad level 3, which is a little bit more refined product. There's also some gridded formats within that message format. But again, a lot of these are all just different flavors of binary encoded formats that we need to write custom readers for and getting it into this common format. So then we also within XRadar, we have these different utilities, for example, georeferencing. Since by default, it just comes in as azimuth around a distance from the radar is sort of the default information. So georeference adds those X, Y, and Z information in there, which is useful when you plot. And then you can also connect to other toolkits. So working with tools like RadLib, this is looking at a ZR relationship, which is a way of relating what's measured by the radar to retrieving like a rainfall rate using information about the scatterers. And then the really nice thing is, then it's sort of in this Pangeo space where we can use all the familiar tools people are used to, whether that's matplotlib or in this case hvplot, and do sort of these one-liners, which we all know and love, to go through and create these different visualizations easily. And then the other nice thing is, so with loading into this data tree and loading within the X-ray space, we can also save to XAR directly and take a look at creating these cloud optimized radar formats, which can be quite a bit faster, quite a bit better compressed, and enable a lot of the big science and just big data set science that Pangeo community people are working on. So on the PyArt side, we're planning on, we're pushing for 2.0, really kind of replacing that core radar object with XRadar here, and basically making the X-ray object the main object people are passing around, working with, and using within the toolkit. So you can see sort of the high priority items there. So using XRadar, integrating with some of our other toolkits, improve references, as well as a new user guide, and then really expanding the IO support through XRadar, some new classification schemes, as well as some new gridding techniques. And really the main story is replacing that radar object with XRadar. So yeah, what's next? So new readers. There's a few more readers. Like I mentioned, we had 13 of those radar formats in PyArt that we still need to finish up. Creating the accessor like interface, and then looking into cloud optimized, basically creating some specs for cloud optimized radar data, which some of the folks here are already looking into. So I'm just gonna pull this up real quick. So if you go on in the notes, I included a link to the notebook here. I'm going to zoom in, and people can check it out if they want. So I'm going to run their imports right here. So PyArt 1.0 works as follows. So I'm using a sample data set here. This is a CF Radial 1 file. So you see it has that .nc format, but it's a weirdly shaped netcdf file. So we load it into our radar object. So we use pyart.io.read to load that in. Then we have this radar object. And then usually people will go ahead and pass that right into our display. So you can see the pyart.graph.radar display. This is just a display class that then you can display.plot whatever different fields. So in this case, we're looking at corrected reflectivity. And that gives you the nice matplotlib plot with the different title all ready to go, your color bar, so on. I use the color bar, colorblind friendly color bar here. And that's sort of the main workflow is you get into this radar object, you pass around to some of these helper classes to then do your analysis. The radar object is loaded with different fields and different attributes that help PyArt know what to do. And the data is stored in the radar.fields, and you'll see this is a dictionary of dictionaries, where we have our data stored in this masked array. We have our different attributes, units, and so on. So that is the core object that people work on in sort of PyArt 1.0. And next, so XRadar is using Xarray. So here, instead of pyart.io.read, when we import XRadar above, it gives us access to all these different backends. So in this case, this is a CFRadio1 backend. So we just specify engine is CFRadio1. And then since these are all different groups within the file, we have to specify that we want group 0 if we're working with just a single X-ray data set. Otherwise, we can load on the full volume. So this is going to load it into a data tree instead of a data set. And we can use open xradar.io.open CFRadio1 data tree to load that in. And then you can see the data tree. So we see our radar parameters, we see our georeferencing, and then we can see our sweep 0, which is the first elevation. And then we can dig in, look at all the different variables that are stored here. So it gives us that nice interactive REPL, which we can interact with. We can do some data cleaning. There's some duplicate arrays here. You can do a georeference. So this is one of the accessors within XRadar. So you do .xradar.georeference, and that adds your X, Y, and Z, which were not there before. And then we just create our plot. So you can do your data tree. You grab your sweep 0. You grab whatever field you're interested in. We call that plot because it's just an X-ray data set, and we can use our that notation there. So we set our color map. We use our vmin, vmax, and we get the nice plot here. And again, the nice thing with this all being X-ray is then we can do the classic .cell or .icell. A lot of these things that we get out of the box, we don't necessarily have to implement that on our own as a library. We can use these common tools and use the common data structure there. So here, this is grabbing the northwest, which with the radar data, straight north is 0 degrees, and it goes clockwise around until you get to 360. So 315 would be that northwest section. Basically, we're looking here to be cutting across here. So we can do .cell along that 315 degree azimuth, and that gives us these quick plots, which again, before with PyArt 1.0 would require creating some NumPy searches and really digging into those arrays to find it, versus with the X-ray approach here, we can use sort of some of these tools people are familiar with. This example of just common data models and being able to use the suite of tools, which is common across the Pangeo space. So in this case, we're grabbing that array we were just working with. This is the reflectivity array, data array. We can use the radlib accessor .wrl.zr z to r, and this is applying ZR relationship or ZS relationship to estimate snowfall, which we just apply that the accessor here. It applies that to the array. We update the attributes, and then we can plot that right back in. Or we could add it back into the data tree as below. And then, so currently within PyArt, we're testing this out and basically have the XRadar class here, which adds the additional methods that are necessary for it to be compatible with the existing functionality. We load that in, and that will basically convert it across and make it compatible with the current suite of tools within PyArt. You can see the representation there. We can grid it up using PyArt here. This is gridding it to a Cartesian grid. Get it back, and then this is the gridded field. So in that case, we were using XRadar to read it in. We're using radlib to do some sort of retrieval, and then gridding up using PyArt. Which makes it a lot easier than having to like save files, use one toolkit, save files, load it back in, and pass things around that way. And again, one of the best parts here is that we get these HoloViz tools or just these other Pangeo space tools right out of the box, where this is just doing a .hvplot.quad mesh to visualize that same field where you can dig in and look at some of the data sets here. We can look at our snow plot and then do like a side-by-side comparison where this syncs up the two. Or say we want to dig into some of these higher areas and look at some of those relationships. So that was a lot very quickly, and I encourage folks to check out. I'll post the link to the notebook again. You can, if you go on to the repository, and this will launch onto the Project Pythia infrastructure. You can go through and try this yourself if you click the little rocket ship and launch binder. Yeah, I encourage folks to give this a try. You can see the associated citations for the different toolkits listed there, as well as the data set that I covered. So at this point, I will go ahead and stop sharing my screen and open it up for discussion. But I appreciate the